Hi, my name is Micki Josi, and I'm a math teacher at Portland Community College and Clackamas Community College. I also do some private tutoring on the side, and I've been working with some sixth graders on adding and subtracting fractions. And so there was something that I noticed that I just found fascinating, and I wanted to just share about this. So first thing that I always like to have students do is create like manipulatives, because one of the biggest misconceptions can be if we are adding, let's say, 1/2 plus 1/3, sometimes students will think just add the numerator and denominator. But in fact, we can show this would not be 2/5. Okay, so if we add it incorrectly without getting common denominators, and then we can use, this is just an online fraction strip. So you could literally search for fraction strips. And I often will have students, on my website, I have a full page of these like in full color that you can print out. But this is kind of nice because you can actually use the fraction strips and manipulate them by just, well, dragging and dropping them. I just took screenshots here, but you can see about the size. So then we talk about, well, why do fractions actually need common denominators in order for us to add them? And sometimes students will say, well, because they have to actually be the same size piece. Here we can see 1/5 plus 1/5 is 2/5, and we can actually count them because they have the same denominator. But the problem is with 1/2 and 1/3, they don't have the same denominator, and that makes them different sizes. And the size comes about from the fact that we're dividing two different numbers. Actually, a fraction is a division problem. But what I wanted to talk about, what I wanted to show is this example. I asked the student, okay, if you had 1/2 plus 1/3, what would you do in order to add these fractions? And so this is how she did it. And I found it very interesting. So what they're learning to do when they add, and she wasn't sure how to subtract, but we could basically use the same algorithm. So the algorithm went like this. She started with the denominator 2 times the numerator 1 to get 2 here. And then over here, 3 times 1. So the denominator of the second fraction times the numerator of the first fraction gives you 3. And then she's adding these two numbers. So if you were subtracting, you would subtract the two numbers. So you get 5. That's going to be the numerator. And then in the denominator, you're multiplying 2 times 3, and that gives you 6. So in fact, it is 5, 6 is the answer. Okay, so if we actually look at, oh, I wrote it on the other page. Okay, if we look at how do we model this with the fraction strips, we can see here that 1/2 is equivalent to 3/6. And then we can see here that 1/3 is equivalent to, is equivalent to 2/6. So another way that some students have learned to do this is by saying, okay, 1/2 plus 1/3. I say some students, probably most of us back in the day, right? Before Common Core, I guess, I don't know. And then we would say, okay, what's the common denominator? The lowest common denominator, which is the same thing as the lowest common multiple of 2 and 3 is 6. So then we would say, okay, I have to make an equivalent fraction. I'm going to multiply this one by 3/3. That gives me the 3/6 that I'm seeing here, right? 1/2 is equal to 3/6. And then if I multiply this fraction by 2/2, so essentially I'm multiplying by 1 whole. Because 2/2 is the same thing as 1 whole, we get 2/6. And then we can look at the picture here, and I can see that 1/3, 1/3 is equivalent to, we call this an equivalent fraction, to 2/6. And so when we add those, the denominators are the same, which means that we have the same size piece. So how many of those pieces do I have that are size 6? I have 5/6. And hopefully that's the idea behind the fraction strips. We can see those equivalent fractions, and then we can add them all up once we have the common denominator. Okay, so what ended up happening when we used that 6th grade algorithm, right? It gave us the same exact answer, but nowhere in this process, I don't know that students are making the connection that they're actually making the common denominator. Here's the common denominator. By multiplying by 2 and 3, you get the common denominator 6, because 2 times 3 is 6. And their lowest common denominator or lowest common multiple is 6. But the equivalent fractions happened here. Okay, you had 3, 6, and then 2 was the numerator, and the common denominator is 6 because you're multiplying theirs. So there's the 2. 6 equals 5, 6. And that's totally fine. I am a fan. Sometimes algorithms are really helpful. An algorithm is just a procedure. It's just the only concern is, what if the numbers are really big? So I just want to give an example that might be more easily understood with the fraction strips, with the visual model, because that algorithm, it will always work. But what you're going to find, if we try the algorithm, let's try the algorithm first, and then we'll recognize how we might be able to use equivalent fractions instead. So like, for example, here, if we were going to use that algorithm, we would start with 12 times 1 gives us 12. And here, 5 times 6 gives us 30. So our numerator is going to be 30 plus 12, that's 42. And then the denominator, we are going to be, and if it was subtraction, we would just subtract those numbers. If this was subtraction, this would be subtraction here, okay? Then in the denominator, we're multiplying, and we get 12 times 6 is 72. And then we have to start simplifying. And this is where it actually became quite tedious for the student, because these are big numbers that we had to multiply, and now we have big numbers that we had to simplify. So her favorite way to simplify, which I loved that she brought this up, was to find the greatest common factor. And we actually used prime factorization. So I'm just going to show that model. So we had 42. She took the prime factors. Well, she actually just factored the numbers. So 42 was 7 times 6. And then 7 is prime. So we're doing prime factorization. That's one way that we can simplify. You could also notice they're both even, take half, half. That was another way that we did it. Okay, 6 is what do we call 6? 6 is composite. So it can break down into 2 times 3, which are both prime. So 42 is, 42 is equivalent to 7 times 2 times 3. And it kind of annoys me a little bit that they're out of order. So I'm just going to stack them in order. Okay. So those are what we call the prime factors of 42. Then we're going to do the same thing for 72. So 72, you can start with any two numbers that multiply to 72. These are what we call factors. You just are going to start with two factors of 72, and we're creating a factor tree. So one thing that I have another video on divisibility rules. So one thing we talked about was 7 plus 2 is 9. So 9 goes into 72. It turns out that all multiples of 9, the sum of the digits add to 9. I'll link that video in the comments, okay? Or whatever, in the description about the 9s. But we can go 9 times 8, and then these are both composite numbers. So we break down all the composite numbers into primes. And 4 is composite, so we break it down into primes. So the prime factorization of 72 is going to be 2 times 2 times 2 times 3 times 3. Those are all the prime numbers. And if you multiply 2 times 2 times 2 times 3 times 3, and we could talk about exponents, we won't right now, then you would get that product, right, of 72. So these are the prime factors, prime factorization. And we can look and see what prime factors they have in common. So I'm just going to highlight them. They each have a 2. They each have a 3. And it looks like that's actually it that they have in common. So since these are what they have in common, 2 and 3, we can multiply 2 times 3, and the greatest common factor is going to be 6. So if we go back up here, if we divide the numerator by 6 and the denominator by 6, then 6 goes into 42. Well, actually, we can see it right here. 6 times 7, right? Because 42 over 72 is going to be 2 times 3 times 7. And 72 is going to be the 6, right? That's the same thing. And then the leftovers, 4 times 3, which is 12. Okay, so we would have 7 over 12 would be the most reduced because every common factor has been reduced. And don't be confused here, I just did 2 and 3 and 6. It's the same thing. I could have done it as prime factors. Okay, so that fraction would reduce to 7/12. And since there's nothing that they have in common in terms of factors, that's fully reduced. That makes sense. Okay, so that was the hard part of this, was once you get those big numbers, then you have to break them back down in order to simplify. What if we were to try this problem, okay, using our fraction pieces? So right here, I'm representing, because I have 5 of the 12ths, I'm representing 5 12ths there, okay? And then with the fraction pieces here, I'm representing 1/6. And then we might think about, okay, is there a way to make them the same size, right? And purposely, I'm lining up the 1/6 with 2 12ths. And so we can see that equivalency. If I multiply by 2 over 2, I'm going to get 1/6 is the same thing as 2 12ths. And the idea behind the fraction strips is then we can actually really see it. Okay, so if I say I'm adding 5 12ths plus 1/6, instead of doing that multiply across, okay, we can recognize that 6 is a factor of 12. So actually the greatest common factor between 6 and 12 is 6. But that means that 12 is also a multiple of 6. So if I multiply by 2 over 2, getting that equivalent fraction from our strips, we have 5 12ths plus 2 12ths. And if we add that together, because we have common denominator, we get 7 12ths. And I asked my 6th grader today, I said, which procedure do you find easier? This way, with all of that, which is great. I mean, this is wonderful math to be able to do. It was a little bit tedious, I will admit, okay? Or would you prefer to do it this way? Or which way do you think is easier? And I think it's like, really in math, we want to find those paths of least resistance. And the whole idea here is that we can understand too that we need a common denominator and that there's different ways to find those common denominators. So hopefully this is a kind of a good video for you to understand the connection. And I have lots more fraction videos, so just feel free to let me know and I'll link some of those in the description as well.